Okay, so guys, vector algebra revision. That's everything that you should know about vector algebra, but you were afraid to ask. That's also one lecture that summarizes the 7 shorter lecture sessions, shorter and longer lecture sessions we had so far. So let's go ahead. First thing is quite easy. Because that's the fundamental question, what is a vector? Okay, and a vector is in fact not this, not an arrow, it's this, a collection of numbers. So a vector is, for example, 3. Of course, vectors may be of various dimensionalities, but in this module we constantly see vectors. And that's the 2D vector, so 2 numbers together, 4 and 3. If we have numbers like this, we can represent them in the coordinate system, and this representation is based on the difference between the end position and the start position of this graphical arrow representation of our vector. So it doesn't matter that it starts at the x-coordinate 2 and ends at the x-coordinate 6. What's important is that the difference between 6 and 2, so 6 minus 2 is 4. And similarly in the y direction, that's 4 minus 1, it's 3. So that's our vector 4, 3. Vectors represent relative positions, not absolute positions, so it's always about the displacement of the end of this vector in relation to the beginning point in this graphical representation of a vector. Now, the graphical representation is quite useful if you want to calculate something that is quite often called the length of the vector, and the proper name in vector algebra is the magnitude, but magnitude and length is the same thing indeed. So if you have these distances drawn here, that's the distance of 4, that's the distance of 3, they all together with the vector v create a right triangle, and from the Pythagorean formula we can find the magnitude of vector, which is symbolically shown with these vertical lines. 4 squared plus 3 squared is 25, square root of 25 is 5, we have the magnitude of 5. Next thing is normalization and normalized vector. Normalization is just creating a short vector of the magnitude 1, like this one here. And we can get it, why I have this, sorry, a short technical break. Oh, okay, then this is better. Okay, so let's go back to, sorry. Okay, so once again, the normalized vector is a vector which maintains the same direction, but its magnitude is changed to 1, and we can get it by dividing the vector by its own magnitude. So 4, 3, that's our vector, divided by its magnitude 5, we get 4 fifths, 3 fifths, or 0.8, 0.6 in this case. That's the normalized vector. For long vectors that have magnitude longer than 1, it would be scaling this vector down. For shorter vectors, because vector may have a magnitude below 1, lower than 1, it will be scaling this vector up. Basically, it's scaling this vector, no change in the direction, but change in the magnitude to 1. And next of these initial topics is vector direction. So we quite often define vector direction in vector algebra by providing the normalized normalized vector. But that's not the only way of providing the direction. It can be also provided directly as an angle, and this angle can be found as a tangent of y over x. In this case, it will be 3 over 4. If that's the tangent of the direction vector defined as shown in this picture. And here is a quick summary of basic vector properties. So you have the formula for the vector, the formula for the magnitude of this vector, the formula for normalized vector, and the formula for the direction angle of the vector. Yeah, so that would be a very quick summary of the basic vector properties. Now, normalized vector preserves direction but loses magnitude. Magnitude is always set to 1. 1 doesn't matter because 1 multiplied by any other number leaves any other number. Okay, 5 times 1 is still 5. So magnitude doesn't count in case of normalized vector, but normalized vector has a direction. And now magnitude does not have direction because it's just a number. Therefore, a vector is a combination of magnitude and normalized vector. And this combination can be shown very simply as a mathematical formula. So a vector, it's this thing, this symbol is the magnitude of this vector, and this thing is the normalized vector of this vector. So if you take the normalized vector, multiply it by magnitude, you get the original vector. Magnitude of normalized vector is always 1, and we will also mention normal vector here. And as I explained several times, people quite often confuse normal and normalized vectors. It's just because normal is a shorter word, but technically they mean two very much different things. And my apology for this, but I also sometimes, when not concentrated enough, I tend sometimes to call the normalized vector a normal vector. So what is normalized vector? I've just explained. What is a normal vector? It's a vector perpendicular to a surface, and it is usually normalized. In mathematics, it should always be normalized. In non-mathematical, not strictly mathematical, so technical, like in development programming, we tend to call any perpendicular vector a normal vector, even if it is not normalized. And the reason for that is that if you have a non-normalized perpendicular vector, which is mathematically not a normal vector, it can be very easily made normal by the process of normalization, so dividing it by its own magnitude. In computer graphics, it is widely used for lighting and calculating the collisions. And example of a normal vector you will see in this revision presentation in one of the final slides. Moving on to displacement vector. Displacement vector, I hope that Zara will provide you with a lot of examples of finding displacement vectors, because nearly every exercise, every question in the first day test will require you to find the displacement vector first. And one of the most common mistakes people do when completing test papers in vector algebra is that they forget about finding the displacement vector. They take absolute coordinates most often, okay, instead of the displacement vector. So we have this coyote at the coordinates 7, 1 and the roadrunner at the coordinates 2, 3. Where is roadrunner relative to coyote? Okay, and the answer is roadrunner minus coyote. So that's the displacement vector, and the displacement vector is always the coordinates of the destination point minus coordinates of the source point. So in this case, it's 2, 3 minus 7, 1. We have -5, 2. Subtraction of vectors is just component by component. So we first subtract x's. 2 minus 7 is -5. Then we subtract y's. 3 minus 1 is 2. Done. So displacement vector tells the relative position of objects. Relative position is in many cases much more important in vector algebra than absolute values, okay, and displacement is equal to destination minus origin. Next topic, vector addition. We actually have just done our simple vector addition because subtraction is actually addition of an inverse vector. But anyway, let's have a quick look. We have the same vector we used to answer the critical question, what is a vector? So that's vector 4, 3, and we will add another vector with coordinates -5, 2. To do this operation graphically, we have to make a small modification to this diagram. We have to move this vector u to the end of the vector v, like this. Why is that? You know that vectors represent relative positions, not absolute positions. So where exactly this vector is drawn, it can be at any position. You just have to keep its direction and magnitude. And now a vector represents displacement from one point to another point. So vector addition will represent two consecutive displacements. All right, but if we had this drawn in this way, we would have like 3 consecutive displacements, because one displacement would follow the v vector. Of course, another displacement would follow the u vector, but you notice that between showing you the v vector, I had to displace my mouse cursor to get to the start of the u vector. So this would be the third displacement. We don't need this, so we rather move u so that to show you, okay, now it's one displacement, the other displacement, and the final displacement is taking a shortcut. So from here to here. So graphical representation of this addition is the red vector v plus u, and calculationally it is, as we explained previously with subtraction, you just add x's and y's separately. So 4 plus -5, it's 4 minus 5, it's -1, and 3 plus 2 is 5. And I'm just noticing in the chat that Zara will highlight negative values and the order of the equation tomorrow in the practical session. So if there are anything unclear still in this, please don't forget Tuesday 11 o'clock the practical session. It's 11, isn't it? Yes, it's 11 o'clock. Vector addition: to add two vectors, add their coordinates. So here is the formulation in the form of a equation: x of the vector v plus x of the vector u, that's one coordinate, y of the vector v, y of the vector u, that's another coordinate. That's the mathematical interpretation of what we have just done. Okay, if we know how to add vectors, if we also know how to subtract vectors, then the next topic must be vector multiplication. And as you probably realize by now, it's a revision after all, there are 3 different types of multiplication of vectors. The first of them is multiplication of a vector by a number. So it's if you have a vector v and want to multiply it by a number n, it's just multiplying the coordinates x and y separately by the number n, like this. And graphically, that's a vector v, that's the double vector v, 2v, and that's the triple vector v, triple v. Multiplication of a vector by a number is the simplest way of multiplying involving vectors. So let's go ahead to dot product of vectors, a very important term in mathematics, vector algebra. computer graphics, games development. Okay, that's quite crucial. So you really need to know and understand what a dot product of vectors is. First of all, unlike multiplication of a vector by a number, you multiplied a vector by a number and you got another vector, longer or shorter, but a vector. Dot product of vectors takes two vectors, but the result is a number. And it's quite important to remember, the dot product of two vectors is a number. Now, how to interpret the dot product graphically? We have these two vectors, v and u, and we create something that we call a projection of a vector v onto the direction determined by the vector u. We will be talking about projections a little bit later because we once had an entire lecture session about projection. I will try today make the projection topic very simple and just the essential stuff. But dot product is defined using the projection. Okay, so this projection is here. That's the length. It's not a vector now. It's the length of this edge of a right triangle created here. Please note that we have this right triangle here. So we just create a construction like this, and we can easily discover then that this green distance from, sorry to say this, SOHCAHTOA, okay, from SOHCAHTOA, it's magnitude of v, so the length of the hypotenuse, multiplied by cosine of theta, where theta is the angle between the two vectors. And now the dot product is defined, and this is so-called definition formula. You know that there are also quick formulas for calculations, but this is the definition formula, which tells this is basically the length of this green section multiplied by the length or magnitude of the u vector. So blue times green. Green is magnitude of v times cosine theta. You have magnitude of v and cosine theta here, and blue is the other magnitude. So that's the formula. Okay, that's the definition formula, which is important, but not so much used practically. So if we now know what is a dot product of vectors, and this is the definition formula, another type of product of vectors is cross product of vectors. Cross product of two vectors is a vector perpendicular to both vectors in 3D space. There is some theory based on the rule of the right hand. So one vector times another vector gives you the distance for the third vector, as exactly shown on this picture here. But because we are going to work in 2D only, we are not entering the third dimension, it's of less importance. What's important for you, it's that the cross product is mathematically represented, the value of the magnitude of the cross product is mathematically the area, surface area of this parallelogram created by the v and the u vectors. And the definition formula is quite funny because it's v magnitude of v times magnitude of u times sine of theta. So far it's very similar to the dot product. The difference is that dot product had cosine here, cross product has a sine, and the mathematically purest definition of the cross product of vectors has this funny thing here, which is the mathematical addition just to tell that the result is a vector, and that this vector can point either upwards or downwards. As shown in this picture, it's currently upwards. Okay, but in most calculational stuff, particularly in 2D graphics, you can just ignore this normalized vector, and you can ignore it because the normalized vectors are the vectors with magnitude of 1. So if you just are interested in the magnitude of this cross product, the normalized vector will not change anything. And this is, by the way, not a mistake. It is indeed a normal vector, because normal vector in this case means normalized perpendicular to the plane created by V and U. So it's really a normal vector. It's both normal and normalized. Okay. Moving on to quick calculations, something that I many times called a magic carpet. Okay, a dot product and cross product are powerful because, by definition, they include trigonometrical functions of sine and cosine of the angle between two vectors. And the magical carpet you are looking at provides a quick calculation, and this is how you will be calculating dot product and cross product in the test and throughout your career as a game developer. Okay, dot product is just 2 multiplication and addition. Cross product are 2 multiplications and subtraction. I hope, Zara, that you will get through a few examples of practical calculation of dot and cross product tomorrow. Can you confirm?
Yep, I will do.
That's great, thank you. Can now move on to further topics. Just a quick resume of this. Many of practical uses why we want to find the dot product and why we want to find the cross product are because of the definition, because of it they incorporate the sine or cosine of the angle. But in practical calculations, you will very rarely, exceptionally, and definitely not on first day, you would use the definition formulas to find the values of dot and cross product. You will nearly always use these quick calculations. So these are the most important formulas for you. One more thing, dot product tells you how close two vectors are. So if two vectors are like this, okay, pointing to in the very similar direction, the dot product will be near its maximum value. The maximum value of dot product is if these vectors are exactly parallel, so there is angle 0 between them. And then we have cross product, which tells you how apart two vectors are. So that's the situation. Okay, right angle between two vectors, the cross product will be maximum then. And using these two observations, we can now find out something about parallel and perpendicular vectors. That's an entire separate lecture here summarized in just one slide, but this is exactly what you will need on first day. So how to test if two vectors v and u are parallel, okay? And parallel vectors will have a cross product equal 0. You remember that just the previous slide, cross product tells you how apart two vectors are. So it will have a maximum value if there is a right angle between these two vectors. But this also means that cross product will drop to 0 if these two vectors are parallel. So cross product is ideal to test whether or not two vectors are parallel. Also, I will jump to the third point here, how to test if vectors v and u are perpendicular. Similar thing, but you test the dot product. And again, dot product is maximum for parallel vectors, okay? But it's not very useful to, it's dot product is a very good measurement of how close they are, but it's difficult to say if you have some huge value of dot product. Sorry. It's my throat, sorry. If you have some huge value of dot product, it's sometimes quite difficult to tell is this the maximum maximum value, so they are parallel or not. So we will always use the other product. So to check parallel, you check cross, okay, which should be 0 with a parallel. And to check perpendicular vectors, test if they are perpendicular, you know that the dot product will drop to 0 for perpendicular vectors. And we also have these equations to create vectors that are parallel or perpendicular to a given vector. Please note that there is infinity of possible vectors that are parallel or perpendicular to the given one. And this infinity is shown in these two formulas by this number n. So you can choose any n you want. I don't recommend n equals 0, okay, because this would create a vector 0, 0, which is neither parallel nor perpendicular, no, not parallel. It's just, you know, a special case. A 0, 0 vector doesn't exist in fact, okay, but any non-zero n would do. So if you want to find a parallel vector, you just multiply x and y by the same number. This number n can be negative number, and in this case you will inverse this vector and perhaps scale up, scale down. Anyway, it will be parallel to the given vector. And if you want to find a perpendicular vector to the given vector, you have to do two things. You have actually even three things. You have to swap x and y, okay? Swap x and y. Multiply both x and y by any number you want, okay? That's the n. And then change the sign from plus to minus or from minus to plus for one of the resulting coordinates. So because I can hear it doesn't sound very clear, I will give you an example. Sorry for my mouse-based writing, but if you have our favorite vector 4, 3, then to find a parallel to this, I can just multiply both numbers, for example, by 2, so this is parallel. And to find a perpendicular, let's say I will also use this multiplication by 2, but I have to swap these two coordinates and also change the sign of one of them. So let's say 6, negative 8 will be a perpendicular vector. It doesn't matter which one you change the sign. It could be here. Okay, so negative 6, 8 is also perpendicular. All right, so I think we can move on to solving triangles with vectors. That's a very useful application of vectors, because it can solve typical trigonometrical problems using vectors. Okay, so we have this right triangle with three edges, A, B, and C. A is the opposite, B is the adjacent, C is the hypotenuse. But what's important is that we put here two vectors. Okay, one vector V represents the hypotenuse. Okay, it has to be a vector that has the same direction as the hypotenuse has, and also the same length or magnitude as the length of the hypotenuse. So it has to cover exactly the C edge triangle. What we need must be just aligned with the edge, this edge B here, okay? And when we have this, are based on the definition formula of dot and cross product, but this is a revision, so I will not show you the whole full evidence. Just believe that it works like this, and if you want to know more, look into the appropriate lecture about solving triangles with vectors. But basically the length of B edge, okay, can be get from dot product v dot n. Okay, v dot n. It's important that n has to be a normalized vector, so its magnitude must be 1. But if you have a normalized vector that provides this direction here of the edge b and the v vector representing the hypotenuse, then a single dot product, you get the b value, and a single cross product, and you get the a value, right? So instead of playing with sines, cosines, and so on, you have dot product, which is in fact 2 multiplications and addition, and cross product, which are 2 multiplications, 1 subtraction. Very simple computationally, very simple to calculate in the test, I think, as well. And it's working, okay? No more SOHCAHTOA. Now, what you can do in case your vector is not normalized, you don't have the n vector, but you have any other vector, like this u vector, the answer is simple. Normalize this vector. So instead of v dot n, you will have v dot n over u normal magnitude. So this thing here is de facto normalized u. So normalize the vector, apply the original formula, or apply these two formulas. That's how you can solve triangles with the vectors. The next slide can be called a forgotten slide because it didn't appear in the original Solving Triangles with Vectors lecture, but it's based on the material that we later did, so I think it's not a big addition, and it will be not required on the test on Thursday, so it's not last minute new material. It's rather another way of looking at the well-known stuff. So that's solving triangles with vectors, but with totally vector representations. So what's the difference? The difference is very delicate, okay? Previously, I asked about the length of the B edge of the triangle. Now, I would say, all right, let's imagine that I have the vector B that represents this edge here, and I would like to get the vector formula for B, not the magnitude, not the length of the edge, but the full coordinates of the B edge, right? And let's assume that I have the v vector representing the hypotenuse, the n vector which is placed here, so the b vector which represents the adjacent edge of the triangle, but can provide you with the exact vector formulation of this edge, is nothing else but v dot n multiplied by n. So v dot n is our previous formula, not fully vectorized, so that's the length of the edge B, that's the length of the edge B, and if it is multiplied by the normal, then we have normal multiplied by magnitude, okay? We reconstruct the full vector B. This is how it can be done. And similarly, we can get the vector A if also the opposite edge, or A, were to be represented by a vector, and that's the formula. Next topic is equation of motion. Equation of motion looks like this. That's an entirely vector formula, and it takes three things. Okay, the first thing is P0. P0 is the initial position of a moving object. Then v is the velocity vector, that's the red vector shown here. Velocity vector shows you how far this object goes in 1 second, how far and in what direction. So velocity is combination of direction of motion and the speed, how far you go in 1 second, it's the speed, okay? So if you take P0 and simply add V, so P0 plus V would put you at this place, okay? So it's P0 plus displacement, it gives you this position here, That's your position after 1 second. But if you want to know what is your position, not necessarily after 1 second, but after any number of seconds, you just need to scale this v vector, okay? Multiply v vector by any time. So if you calculate p for t equals 5, you will get p0 plus times 5 times vector v. So it will be somewhere outside of the screen, but it will be your position after 5 seconds of movement. The beauty of this formula is in that you can also substitute the negative value for t, and therefore get your historical positions in time before the object arrived to p0. One important thing is that this formula only applies to objects that are moving along a line, so straight, okay, no turns, with constant velocity. Actually, constant velocity means constant direction and constant speed, so no turns, no acceleration, deceleration. But this is fundamental in our physical simulation next term anyway, so that's the most fundamental, the most important equation for moving objects. Now, if you want to go from vector representation of this formula to number representation of this formula, here it is. Here is how you can find the x value and y value. Using xv and yv, xv and yv are the velocity vector, okay? The velocity vector coordinates. So these are formulas for x and y after some time t, and also the speed, okay, is the magnitude of the velocity vector. And the speed is the numerical value. So remember, velocity is a vector, speed is a number, and speed is the magnitude of the length of the velocity vector. Done this, moving on to equation of motion, normalized direction vector. Normalized direction vector is nothing else but normalized velocity vector. Actually, it's a normalized any vector that is in the same direction as the motion occurs. So in exercises in the test, it may happen that you get the velocity defined as the movement towards some goal somewhere placed in space. And in this case, you can get the displacement vector, which is not necessarily a velocity vector, a displacement vector. And you can also normalize any kind of a displacement vector if it's only a vector that is contained in this line along which the movement happens. Okay, so normalize the velocity vector or any displacement vector, you get the normalized direction vector. You can also recreate any point on the trajectory of our object using this normalized direction vector, but about this in a moment. Now let's have a look at the normalized direction vector itself. It will be called normalized direction if its magnitude is equal 1. So to get it, you have to normalize the velocity or divide velocity by its own magnitude, and the magnitude is given with this formula. Now, what is this thing? P of u equals p0 plus nu. That's a formula which is quite similar to the motion equation. The difference is that working with the normalized direction vector, we cannot calculate the position of the object in time. We can generate various positions of the objects provided various values of this u, but u does not have here any special physical meaning like time, so it's just a purely mathematical formula. Guys, that's everything I wanted to say in this revision lecture. So 7 lectures packed into one, but I think it really makes sense to watch all the 7 individual vectors because you have all the evidence, all the mathematical thinking there, and probably also if I deliver something like this, an hour, 15 minutes, more like an hour, about all these topics together, you would be by the end of this lecture totally confused. So if you did this stuff gradually and you now listened to the revision lecture like this, yeah, it's probably now quite understandable. I hope it is. The last slide, the final slide, shows your formula sheet in which you have all the formulas you would need in the test. So you have the general formula for a vector, displacement as the end position, destination position minus original position, magnitude, normal, vector addition, vector subtraction, multiplying a vector by a number, including the division of a vector, dot product, that's the definition vector formula and the fast formula, cross product, the definition and the fast formula. You can always ignore these normalized vectors, big N's here, okay? A test to find out whether two vectors are perpendicular or parallel. You also have the motion equation, projection formula, and reflection formula together with the applicability condition. That's all for now. Thank you very much for watching, and don't forget to subscribe my channel. Thank you.